So my talk will be about quantum thermodynamics in superconducting circuits. So in fact, I don't know if I will really give you a picture about how this quantum energy initiative will move forward with what I will present, but nevertheless you will see at least some things that are related to, I mean, things that tell you what is actually possible to do in these circuits from the point of view of thermodynamics and thermal measurements. So this work is done at Aalto University, and I already apologize that I will not give a full credit to everybody here in the audience or outside about not citing all the work that you have done, but I try to really focus on things that are close to our own activity. So what are we actually after? So this is kind of the slide which tells what are the kind of quests and what are the questions. So of course we want to understand heat transport, which is basic thing in quantum thermodynamics, and we do it in the circuits. So, and there are several types of carriers. There are electrons, there are photons, phonons, and combinations of them. Then what is important in this thing when we go to small, when we do quantum circuits, is that noise becomes an important factor. So this leads to stochastic thermodynamics, which is a field that is very well known in classical world, fluctuations in general, and information and feedback. So in fact, this is how one can go to Maxwell's demons and things like this. I'm not going to talk about Maxwell's demons today, although we worked on that like a decade ago quite a lot. We want to understand decoherence of qubits and thermalization in isolated systems, because this is, and also in open systems. So this is of course important because this is something that actually could hold together the quantum computer if there is no thermalization. We want to build useful devices. We have done something, and I will tell about them. Heat valves, rectifiers, refrigerators, of course. Engines we didn't do yet, masers, spectrometers, I will tell you, Maxwell demons, and detectors with very good resolution because we work at very low temperatures. And we want to harness thermal fluctuations for Brownian refrigeration, which I will tell you about that today. And this is maybe close to the quantum energy initiative as well. And then tools for all this. So this is a very long list of things that I will kind of cover. Don't get scared because they all connect to each other somehow, and it should be a continuous story in a sense. And I will tell you for the first time at least about two different topics. That we have some experiments now on quantum interference of heat, and also a long short experiment of seeing how you can utilize noise in cooling. This is something that I will also tell. So one of the objects that we look at is naturally a qubit. And qubit, what it is actually in the simplest representation, it's just a Josephson junction. A junction between two superconductors with an insulating barrier in between. And it has a circuit interpretation where you have these two junctions. Actually, this is usually, or often it is built of two parallel junctions in order to be able to control it by magnetic flux threading through it. And it has also a capacitance which gives another, besides the coupling, Josephson coupling, the capacitance gives you the kinetic energy, the capacitive energy of this system. So this would be kind of the fully isolated system. But in the real world, of course, things are connected to the external world. And this means that we are talking always about open quantum systems, although we, of course, hope to have sometimes systems which are as well as possible isolated from the external world. But in many of the experiments that I show, we intentionally connect these things to the external environment, so we kind of destroy part of the coherent properties of these systems. But this allows us to look at how energy is transported between the quantum system and its environment. So what one can do, actually what we have is we have these qubits here, and then we have the environment. So conceptually, it looks like this, essentially. So now, this is our system, and this is the environment. We can model this in many ways. I will tell about this as well. But what you want to do is you want to look at the system, and you also want to look at the environment. The good thing here is that the environments are usually small, so small in a sense of heat capacities. They are actually quite weakly coupled to the real external world. So in this case, these environments can also have their own dynamics. And they are not real baths because the temperature is not fully fixed. So we can have microscopes for different parts of the systems. I'll start from this part very briefly, because this is not what we have been doing very much, but what we have gone into recently. So how do you look at the system? You can use the standard things which are really widely available these days, looking at qubits, looking at quantum circuits by different RF techniques. And what we have done, and I just don't stay on this topic long here now, I just tell you that it's possible, for example, by addressing these qubits, which are, here is, for instance, one of the transmon qubits, which is connected capacitively to the controls, and then it has a squid, which is actually the thing that can through which you can control the energy of the qubit. So you can control this with the RF pulses. So you can put pi pulses to excite the system, and you can look at its evolution. So this way you can have, as I said, you can have a microscope of this system. And what we have done about this recently is that we are using the 3-level transmon qubit in order to do thermometry. So it is possible. Although you would say that qubit is it's just a 2-level system, in this case a 3-level system, it actually doesn't have its own temperature, but as a qubit, it is looking at the environment that it has, and it's probing the temperature of its environment. Okay, but most of the things that we have done up to now is about looking at the environment, and this is what I talk mostly today about. So what does it mean looking at the environment? It is to look at the baths, which in our case are usually electronic baths, like resistors. Here we see a resistor which is often made of copper, sometimes made out of chromium if you want to have it more resistive, or whatever metal. And it is probed by something that I will tell you later on about. And now this kind of electronic system here, it is a system which you can tell that it has a temperature because it has typically billions of electrons in this, and they are forming, of course, in the equilibrium, they form a Fermi Dirac distribution. Now, depending on what it is subjected to, what sort of heat currents, what sort of reservoirs, what sort of couplings, its distribution is determined, and this distribution is the electronic temperature typically. So the nice thing when we are working with the metals is that, as is known from experiments already for a long time, is that electrons in these systems, although they are rather free electrons, they still talk to each other fast, so that the internal relaxation time is of the order of nanoseconds, whereas the coupling, for instance, to the phonon bath is much slower. It can be like hundreds of microseconds at low temperatures. So we really have a well-defined temperature in these electronic systems for most of the time. So now what you do is you want to look at this system's temperature, because this is what tells you what is going on around it. So, for instance, what we can do is so-called bolometry. And bolometry is a simple thing which tells you that if you have this kind of a system, like this electronic resistor here, and if you have some heat input, let's say you have a constant heat input here, and this small system is connected to some sort of superbath, which can be the phonons in this electronic case, or the photonic bath, whatever it is, and it is connected to that with a certain thermal conductance, G thermal. In this case, what happens is that you can determine, you have a meter for heat current by measuring the changes of temperature by a sensitive thermometer. So the average change of temperature is given by the ratio of the heat current to the thermal conductance in a linear response. Of course, if you have a fast thermometer, you can also see some variations, and I come back to that later, because this is called calorimetry then. So what we use in the lab is just a very, this is kind of the bread and butter in the lab. So we are using a probe thermometer, which is a tunnel junction between a normal conductor and a superconductor with a thin insulating layer in between. Its transport properties can be measured in a very, very basic way, and what you find out is that since we have a superconductor here, it has the BCS, Barden-Schrieffer-Cooper energy gap. That's why at low temperatures the current voltage characteristics looks as shown here. So now, if you are at low temperature, there's a threshold which is given by this energy gap of the superconductor. So, but it's not exactly like this, because at higher temperature, you have the distribution, as I was explaining, and then the current starts to flow a little bit below this gap, and also it's smeared all over the place. So in this case, what you have is that, and here is another junction here. So what you have is that this current, which is running through this contact here, can be written in this very simple integral form, which is kind of a Landauer form for the electrical current through here. And you can see that this thing depends on the distribution of electrons here at the energy which is given by the actual energy plus the I mean, it depends on the voltage across the junction. And then you have this density of states of the superconductor, which is essentially temperature independent. So this is a probe of only the normal part here, since this we can forget for most of the time when we are well below the superconducting transition temperature. And one can, in fact, derive a very simple form for the current versus voltage below the energy gap delta of the superconductor, and it is even a primary thermometer if you really make it perfect. You can say that this logarithmic current versus the voltage is really given by the 1 over kBt times the electron charge. And this is it indeed. If you do a well constructed experiment, you can demonstrate this. This is all very well known, but in general, we don't really rely on this primary feature. We usually calibrate this thermometer and measure, in the simplest case, just voltage at a constant current. So what we can use this for, and now we come to the part of kind of quantum phenomena with this system. So we can put, for instance, this is kind of the archetypal thing. We did it several years ago, but I think this is maybe the very illustrative experiment for the principles. So you put here the quantum system, which in this case was indeed, it was the simplest transmon qubit, which had a squid so that we can change the energy of the qubit here. And it was connected capacitively, so there's no direct electronic connection between these two ends of the system. And it's connected to what we call a coplanar wave superconducting resonator, which is just a harmonic oscillator close to its resonance frequency. And then at the ends here, at both ends here, we have resistors, which are our mini baths of heat. So here we have a 3 micrometers long copper resistor at both ends of the system, and it is tapped with these tunnel junctions. This can be used for both controlling the temperature here by joule power and also measuring the temperature here. So what this system does, because we had these 2 harmonic oscillators around the qubit, which in some approximation, we can approximate this qubit by a harmonic oscillator whose inductance we vary by the magnetic field. So now the system looks in the electrical engineering picture, it looks like this. We have this bath here, resistor, which produces Johnson-Nyquist thermal noise here, and we have another resistor, which is maybe at the low temperature, and it also produces a little bit less Nyquist noise here. So now, when we have this temperature bias, which we created by joule power, for example, over the resistors, then what happens is that this, if this qubit here is detuned from the resonators, then there is no power, but you can change it by the magnetic field, and in this case, you can let the photons from, let's say, the electrical noise or photons to traverse from one end of the circuit to the other. And what it leads to is that, okay, here is the picture, not in the electrical engineering matter, but from the open quantum systems point of view. You have the qubit here. It is coupled by these capacitors to the resonators, and then these resonators have another coupling, which is essentially is the quality factor of these resonators, which tells us how dissipative the resonators are. So now, now this qubit is coupled to both resistors here with some sort of Lorentzian filter, and then what happens is that when you change the energy of the qubit, which changes periodically with the magnetic flux here, you can see that the power, which we measure exactly the way I was explaining, measuring the temperature of this absorber as a function of this flux, shows you that there are like two points within a flux period where it maximizes. And these 2 points correspond to the situation when this qubit has the same energy as the two resonators. I will come back later to this other part here, because you can also cool this resistor here, and then you can reverse the power from going from this distant resistor to this one. So these were physically at a distance of about 4 millimeters, and there was no direct connection between the two. In some cases, I will come back to this maybe not so much, but you can also describe this system as a combined system, or hybrid system, where you have these resonators and qubit forming the combined quantum system, and these are directly connected to the two resistors then. In this case, the flux modulation looks much more complicated, but that can also be modeled, like in this case as well, by a simple master equation for the system. So now I will show you several other examples of how to use this bolometry in these experiments. So this is, I will focus on, in fact, 4 of those things. This one I will not tell today about, but we can talk about separately if you like. And I'll just start with this, because this is not a long story. I'll just tell you that now we were working in the previous experiment with a transmon qubit where the coupling to the bath was very weak. But now we can use what is called a flux qubit, or superconducting flux qubit, and the flux qubit is shown here, where we can connect directly galvanically the magnetic flux, which is induced by the noise of these resistors here, to the squid of the qubit here. So because it's galvanically connected, the coupling can be much stronger. So in this case, for instance, one can get to something like 10% coupling of the energy of the qubit itself, whereas in the other case it was of the order of 1% only. But the measurement principle here is exactly the same. So we can heat or control the temperature of one of the resistors and measure what happens at the other end of the system. So now, of course, one can do different experiments in this kind of a system. If you measure the RF transmission, if you connect there you put there kind of the standard spectroscopy measurement where you measure the transmission in a coupled transmission line here or waveguide here, and look what happens when the qubit is tuned. What you will see is that there are 2 peaks here outside the minimum of the energy of the qubit. What happens when you look at the heat transport is kind of complementary to that. So what you see is that there is a kind of a triplet there. There are 3 peaks, the central peak, which is not in the RF transmission, and then there are these 2 side peaks. And this was something that puzzled us for some time. but it turned out that it is quite clear where it comes from. So first of all, the system has, of course, it has this these avoided crossings here when the qubit energy and the resonator energy are degenerate, and in this case you get this. You get these side peaks which are showed here for the transmission here. But then what happened in the thermal experiment indeed is this central peak at this point when the flux is at the value where the energy is minimal. And this means that there is a thermal excitation of the qubit and at this energy. And we can model this system as well by assuming that we have this resistor which is sending the energy to the qubit through this transmission line, which is essentially could be again discussed as a harmonic oscillator. But we went one step further and we discussed this properly as a transmission line which has several resonances at different frequencies. First of all, what we obtain is that we see that there are these side peaks and the central peak, but if one looks at the data very carefully, you can see that there are also some extra peaks here at frequencies of the qubit which are outside this triplet that we see here. And this also can be reproduced by the theory. Not reproduced, but let's say that we can see similar peaks there at those points. So this was about the quantum heat transport as such. Let me now go to experiments where we involve also some dynamics more. So this first experiment here, which I show, is actually still a passive experiment where we are measuring something which is actually puzzling, I think, many people still in this community, is that what happens to for instance, to an array of Josephson junction when it is biased, voltage biased, when this Josephson junction array becomes dissipative. So you know that if you put just a current through it, basically you can have a current without voltage, but if you force a voltage bias across, there is some phase dynamics in this system, and when the phase is not constant, it means that you also need to somehow dissipate the energy that you are generating by this voltage times current through of this circuit. So the question is, can we really do some diagnostics of this by looking at by bolometry outside the array? So if you take a long array, we started with about 800 junctions in series, and you look at the current voltage characteristics in a small bias range, it looks just difficult. I mean, but what the thing is that as soon as you go away from zero bias voltage, you start to generate heat in this system, and it has to somehow be evacuated from the system. It can go to the phonons, but this is a very weak process. It can go outside by radiation, but there are many junctions in the array, so it's kind of a complicated issue. And that's why we wanted to start from something much, much simpler in the experiment. So what we did was that we took just a single Josephson junction. So this is kind of the simplest experiment you can do. So you take a single Josephson junction and you put a resistor outside it, and you voltage bias the junction. What happens when you bias this is that actually you are tilting what you could call a wash-pot potential there, so that there is the phase which is running in this junction. It is, as a function of phase, there is an energy landscape which tells that there are minima, but there is a possibility to jump down, and each jump down corresponds to the dissipation of energy. So this is an experiment that we did, and I must advertise here that there's an experiment here in Grenoble by Clemens Winkelmann and his collaborators, where we little bit participated as well, which was about this very similar effect in normal superconductor SNS Josephson junctions. but I focus on this experiment that we did here at Aalto. So in this experiment, you can see it looks a bit complicated, this setup. So we had a single, still it looked complicated. We had a single Josephson junction in the center, and then we had 2 bolometers outside. Why 2? Well, it's just for checking and for symmetry of the structure. And again, we had all these same bolometric detection techniques outside there. So now we can voltage bias this, and we can measure both the temperatures, and we can also measure the current voltage characteristics of this thing. It came as a surprise that the picture looks very complicated. And I have no time to go to all the detail of this, but I just tell you that when we look at the temperatures of the 2 resistors here as a function of voltage, you can see that they show very similar features. So these are the data taken at different bath temperatures, starting from about 30 millikelvin up to about 300 millikelvin here. And there are several features in this which kind of correspond to what you measure also in the current voltage characteristics. But there's, first of all, there's Joule power in the resistors itself due to the current, which is just seen here at small bias range when the junction itself is non-dissipative. But then there's a very large increase of temperature at a certain range, and this cannot be explained by just this simple DC IV characteristics that we measure. It corresponds actually to what we have at the large currents, which produce about 100 times more power overall. So in this range here, which is in between about 100 and 200 microvolts in this case, what we see is that the heat is indeed, it is radiated from the Josephson junction. And what we could model this with was very, very simple thing. So we took a junction to be represented by a AC current source, which has the current which is given by the phase sine phi times the critical current, and this phase here is now running due to the voltage that we are applying across. And then there is an AC current which is generated in the circuit, and this has an effective value which is IC squared times resistance over 2. And surprisingly, we could see that in this range of biases, it's really nicely captured this overall magnitude by this very simple expression. There are some oscillations here which are coming from the fact that this system has some resonances on top of the thing that it just doesn't transmit everything that we put into it. But the nice thing here is that it's a detector which can run up to about 100 gigahertz, because the voltage that it corresponds to here is about 100 gigahertz for Josephson junction. Okay, now I come to something which is as I said, new and we didn't present up to now, and this is quantum interference of heat. So this is our. Let me start from something. So we start now to go to the situation where we are doing AC drive to our quantum system. So up to now, everything was driven just by temperature differences, or we were looking in general static properties of this bath. But now let's start first with a simple case that we have a drive on a harmonic oscillator. So let's take just a resonator, just an LC oscillator here, and we put an AC drive here on the system. This is this part here. And then this resonator is now terminated again by a resistor. In order to have a bit weaker coupling to this resistor, we put a small capacitor in between the resonator and the resistor, and this gives us the quality factor of the system. So now what we are doing is that as soon as we are driving this, we populate this resonator with photons, but it reaches kind of a steady state, and then the photons are leaking to this resistor here. And it's a very simple system, so you can either analyze it by just classical means, or you can write a master equation, assuming there are several baths there. But what you find is that the power to this bath here is given by some what is related to the driving amplitude, and then the quality factor QK, which is the quality factor to this bath here, and then the overall quality factor of the whole system. So this gives us a nice spectrometer, actually, a thermal spectrometer. So when you compare it to the standard spectrometer, this is of course not fully fair because this was a very relatively low quality system. So then the standard spectroscopy gives you that you have here the resonance of the resonator, and then you have a lot of background variations as a function of frequency, which you always have, but here they are kind of exaggerated because the resonance was weak and broad. But nevertheless, what we can see that if you do the very simple experiment by running the thermal spectrometer here and measuring the temperature by DC means of this thermometer here, we can see that the thermometer voltage, which is inverse to the temperature, shows that there is a Lorentzian peak here, exactly as we expected here. So that has no variation in the background, and at different powers we get different strengths of these peaks. And typically the spectroscopy is limited by, in your fridges, to the frequencies which are below 10 gigahertz, of course not always, but the standard spectroscopy. But with this thermal spectrometer we could see also the third resonance of this resonator, which is at 21 gigahertz. And overall, we can use it down to almost down to the level of one average photon in the resonator. But now let's go to a more complicated experiment. Let's go to the experiment where we we are driving the qubit, whose energy is then, of course, not fixed unlike in the harmonic oscillator. So now there is a very standard experiment, which is kind of the Landau-Zener experiment. You are driving the qubit around the avoided crossing here, and you pass the minimum of the energy at this degeneracy here. And if you have now a dissipative system, which is connected to a bath, then if you run fast, you will pass to the excited branch here, and there's a likelihood that the system releases energy to the bath. And this is what we can measure. So now what we can do is that you can keep driving the qubit and then measuring the temperature of the bath again. There are predictions which actually did is that there are, and many other people have looked at how this dynamics goes, but we were looking at in particular from the point of view of power that we get to the bath. And we can see that there are these kind of fractional peaks in frequency, so driving frequency, which come from the fact that when you drive the system, the dynamic phase of this qubit is evolving like the integral of the energy difference of this qubit as a function of time. And this energy difference depends on the drive. So you will have, if you, for example, make a small amplitude drive, you will see that you will get peaks at these fractions of this frequency corresponding to the energy of the qubit. So now it is interesting because is this something that really will then eventually affect the efficiency of the heat engines or the refrigerators, their power? And there is a lot of theoretical literature on this from many people, also people from audience here. So, as I said, my reference lists are not exhaustive by any means. But anyways, this is an interesting question in general, is how the heat engines are when they become truly quantum, how they behave. So our experiment in this respect was kind of just initial stage towards this, because now what we were doing, we were driving a qubit which was actually coupled through a resonator to the heat bath. So this you could imagine that this is half of a true heat engine, which is or a refrigerator. If you would mirror this to the other side, you could have a 2-bath experiment where you would drive the heat from one bath to the other. But here we have only one bath, and we are driving the qubit. We are doing exactly what I said in the previous slide, but then it is coupled through the resonator to the bath. The system looks very much the same as in the previous one, but now we are also addressing the qubit here, which is now tuned to the suitable frequency. And the driving is done by the flux bias line to the qubit. So one can characterize this device quite carefully. The Hamiltonian is rather simple. You can get all the frequency, you can get the persistent current of the flux qubit, you can get the couplings quite accurately from the spectroscopy measurement. I will not go into the detail. And the experiment looks, the result looks quite simple. So what we are doing, we have two different, once again, the measured power, we can get it from this coupling to the bath, but we can also simulate this system theoretically because we know how to calculate the power in the open system. This was done numerically because the system is rather complicated, so that's why I don't want to go to any detail in this, because this is kind of, as I said, the first stage. But overall, what you can see is that that experiment and simulation look quite a bit the same. So this is with two different driving frequencies. This is one of this. This is 1/3 of the resonator frequency, and you can see that the powers are actually relatively large. They are almost like 1 femtowatt. There you have the maximum, and you can see that as a function of the DC position of the flux and the amplitude of the drive, you have both in the theory and experiment a pattern which looks rather complicated but looks similar in both cases. You can go away from these interesting resonances, and then you still have a little bit of power, and still you can see that in the experiment the signal is very weak, but the same pattern as from the simulation appears. So this is definitely something that needs much more from the theory point of view to understand all these things. Okay, so that much about that. And then, how much time have I spent? I have 10 minutes. 15 minutes left. Okay, good. So now I go to something which is, one would say, classical. And this is the thing that can you use a thermal? Can you use kind of waste heat, or let's say noise source, to make a refrigerator or an engine? Engines, of course, there are jobs on refrigerators, but on chip, can we do this, that we, for instance, would cool something by having a thermal noise source acting on the system? For us, this system is, you already guess, it's a tunnel junction. So, and this is something that we have been working for many years about using these junctions as refrigerators in general, but not by noise, but by applying bias voltage across such a junction. So similarly, as we were talking about the current voltage characteristic, there's energy current or heat current going away from the normal conductor when you bias it in a position which is close to the gap value of the superconductor here. It's very easy to understand. You just skim off the most energetic electrons from the normal conductor, and due to the internal relaxation, the normal conductor sets into a temperature which is lower. So you can really cool this down, this normal conductor. And the expression for power, the cooling power, is very similar as for the electrical current, except that there is the energy that you take by each electron here when it's biased is multiplying in the integrand here. And when you calculate this as a function of voltage normalized by delta here, and look at the power, you can see that at different bath temperatures, it's always peaking at about the gap voltage, a little bit below, and the higher you go in temperature, it goes linearly away from the gap here. And the power is not dropping very quickly with temperature. It actually has as a temperature dependence, which is proportional to the temperature of the normal conductor to the 3/2. So it's not it's not exponential like in a typical evaporation fridges, but it's rather this polynomial dependent. So it's really nice, and you can also evaluate the efficiency of this process. It's given by how much heat versus how much joule power you apply on this system, the ratio, and you get that it's quite close to kBT or delta for an ideal junction. And this is an effect that we have been working for a very long time on, and already in the very old experiments we could go from, let's say, at non-biased case we were sitting at about close to 300 milli-K, and we could go at the optimum bias point, which is actually symmetric. It's not a Peltier refrigerator. It's a symmetric effect due to the electron hole symmetry in the density of states, and then this value here is about 100. So factor of 3 was quite easily achieved already from the very beginning, and this has been improved over the years by many means. So why I actually want to show this very much here today is that this is something that this Brownian refrigerator was something that Frank Hecking, late Frank Hecking from Grenoble, with whom I worked a lot at the time, we proposed this together at about almost 20 years ago. So and a very simple concept. So suppose you have this junction here, and you have a non-equilibrium resistor. You have a resistor at a higher temperature here. It produces thermal noise, and circuit has, of course, some extra capacitance. So to make the thing perfect, it has its own capacitance, and then the circuits always have some capacitance to model it simply. But when we modeled this system here, we found that when you have the ratio of the two temperatures, there is a curve which looks very much like this voltage-biased system, that there's a maximum of power which occurs when this resistor here is at the higher temperature. Of course, it has to be like this. So you can extract heat from the normal metal at this point, which depends. These different curves are for different values of the capacitance here and whatever the value of the resistor here. So there's actually like two parameters in this simple circuit to vary. And then what we now have done is that we have tried to implement this into a circuit like this. So what we do is that we have a resistor which we now made out of chromium to make it more resistive, because that's advantages here. And then we have another side here which is made out of copper with the NIS junction. And of course there is some capacitance there. We can model this again a little bit better, but just as a simplest model is like this. In fact, all this thing here can be boiled down to the fact that you can think that there is kind of a voltage noise here, and this gives you you will have some sort of a distribution of voltages here, which is driving the energy from the normal conductor to the superconductor. So if you have voltage noise here, it actually is like biasing the system at different voltages at different moments of time. So what we did is that this is quite a complicated sample already made by Bayan Karimi in the lab, and we did the experiments together on this. So here is the chromium resistor. It's here. And then there's the copper here, and then there are capacitors here. So they are really not connected directly, these two sides of the system. But the capacitors are large enough so that for the thermal frequencies, the system they are transparent. The capacitors were made in a very simple way. It was just chamber was opened and aluminum oxidized and closed again. So it's actually, this is easy part, turned out to be the easy part of the fabrication here. And the cooling junction is here. So there are many probe junctions here, and then the cooling junction, which is about 5-10 times bigger than the small probe junctions. We can't measure actually the resistance of this junction because of these capacitors at all here. But the measurement looks quite promising. So this is very preliminary. The fridge is cold at the moment. So this is this is like the temperature of this chromium when we pass the current through the chromium here. And you can see that because it's resistive, this chromium here, you don't have cooling, although the junctions there are quite similar as in the other side here. But you can have almost like a parabolic heating here at the small bias currents here. When you go to a higher temperature, your cooling power of the junctions wins the dissipative joule power here on this, and you start to see cooling also in the local part here, because we have the probes here to check the local ones here. But perhaps the most interesting part here is that really in this low temperature end here, what you can see is that as a function of current, you can see that okay, look, these are these are like thermometer voltages both, so they are not yet calibrated. So going down means temperature goes up. So you can see that here, for instance, that you start at 0 bias current here, and you put on the current either positive or negative. You can see that the system cools down. But when you go further away, it starts to warm up again. Well, this experiment is not yet fully clean because we have a combination of shot noise in these junctions here, plus the noise, thermal noise, which is from the resistor. So I don't want to say that this is a pure thermal noise that is affecting here. It's kind of the two contributions are not very different at these values of currents. And it's also seen that here, when we go to higher temperature, you can see that when this is cooling, you still see the same cooling on the other side as well. So there's a combination of the two effects that we should analyze this better. But nevertheless, this is kind of a promising thing that it seems that this Brownian effect can be used for cooling. Okay, so now my time is, I have 5 minutes. So I will go very quickly to calorimetry, and then I give you some appetizers for future. So I don't say much about this. So our big objective has been to try to make a calorimeter which would be able to measure, okay, there's an arrow missing here. So measure the change of this temperature when you get the impulse of the single photon, for instance. And this would lead to a temperature in time which is first increasing and then it's relaxing back depending on the parameters of the system. This is given by the heat capacity, and this is the combination of heat capacity and the thermal conductance. And this has been done for a long time with X-rays, for instance. But here, if you want to do this with the qubits, the energies are much, much smaller. So the energy resolution becomes a big issue. And for that, we have been developing a sensitive thermometer, which was actually used also by Clemens in the measurements of this SNS facelift experiments. But here, so we are using a tunnel junction, again, between the superconductor and normal metal, where we proximatize the normal metal a little bit. And this gives us a feeble supercurrent at 0 bias. And it means that it is almost non-invasive thermometer. And it is sensitive to temperature because it's a very weak supercurrent. And this we have been measuring not only with DC, but putting it into a tank circuit so that we can measure it fast, up to about 1 microsecond, or down to about 1 microsecond, which is faster than the thermal timescales that we have typically. So now the game is to try to be able to measure the change of this temperature when you get a single microwave photon. And what limits that is the thermal noise of this resistor here. And this is our experiment where we could see that this thermal noise or noise equivalent temperature is not very far from what you would expect from the fluctuation dissipation theorem. And at low temperatures, it means that if we would have like 1 Kelvin qubits, we would have a margin to measure it. Not going into the detail, but that's what we have. So the idea is then to really trying to connect this to the qubit and to measure the temperature in response to this relaxation of the qubit. And it seems we should have a sufficient signal to noise, but we didn't make much progress very recently on this. But now we have ideas how to do the thermometry better by using the cross correlation techniques on the observer. So I will finish just a few minutes by telling what we actually are quite interested about now, to try to look at the thermalization in general. So now let's forget about essentially the resistors we had and think about whether an isolated system could thermalize or not. And of course, this is a topic which is, in general terms, has been discussed theoretically for very many years, and there are also in cold atoms there are some experiments on this already, although not, of course, fully conclusive in all respects. But the thing is that now, because we have already superconducting circuits where the relaxation times are like hundreds of microseconds, even 1 millisecond, we have resonators which have huge quality factors. Is it possible to make systems where the system, you can monitor the system dynamics on the time scale when it is not yet connected to any bath, and can it reach some sort of a thermal distribution? And I will, its time is over, so I will just tell that we analyzed different systems, like making Johnson junction arrays or very long transmission lines, like in the experiments in Chicago, where you can think whether these can behave like things that thermalize. And the answer is actually not really, although this is, of course, these are things that have been discussed a lot, but they are really, they have the resonances in the spectrum, and you always have recoveries from this system, and the qubit never relaxes properly. So what we actually are proposing is that we should you should make environments which are consisting of qubits which have kind of dispersion in the parameters, and in this case you will be able to mimic a thermal bath by them for a qubit. But still there's a question, even in this case, what happens to these environment bath oscillators which we have here? And the answer is that if you look at the long-time behavior of the distribution of them, at least in the weak coupling limit, this central qubit is talking only to the ones which have an energy very close to them, and with this quadratic coupling, it will never, these oscillators will never thermalize as such. But if you allow, for instance, if you allow a cubic nonlinearity in the couplings, then what happens is that you lose the integrability in a sense that you can create a lot of you can really change the number of excitations in your system, and this way at least our simple model calculation shows that having nonlinear systems could be the way for thermalization in an isolated system, and this is something that we might be able to look at in these systems. So just to finish, so I just put here a list which are kind of, to me, the interesting experiments for the future. Of course, this thermalization of isolated quantum systems, which is very challenging. Then making auto-refrigerator, so let's say quantum refrigerator, and see how the quantum interference really would influence it in a concrete system, and how this strong coupling would influence it. Then, no doubt, the single photon detection would be very interesting, because many things follow from that. You can do stochastic quantum thermodynamics after that, and then you can look at how a measurement really affects the system, the kind of the 100 years old problem. And then what I also would like to have is if we can make this thermal noise cooler really work reliably, can we make a practical cooler towards the QEI quest? Yeah. So that's actually, here's the main people from the experimental group. So Bayan has, of course, been Bayan Karimi. She's a postdoc. She's now in Chicago. And then there are several PhD students, Rizab Christophorus and Cheyan, and some seniors, and then like Jonas Peltonen and Yucheng Chang, and then Mitya Vov and Sergey is a PhD student, and Sergey Lemchikov is a postdoc, and then Guan Shun is another postdoc. And of course, we have a lot of external collaborators, but I don't list them all here. Thank you very much.
Thanks, Jukka. Are there questions?
Alex.
Hi, thanks for the very nice talk. I just want to make sure I read correctly. One of your slides was written quantum heat.
Quantum heat.
Yeah, and so and if so, how would you define it? Because I'm not sure.
Okay, we are coming to the.
It was the quantum interference of heat, and
it's an interference
and it slept
of heat.
to quantum heat. So
yeah. Okay, yeah, it was sure. Yeah, one should be careful about.
Yes, absolutely.
Notation. Yeah.
So, do you have a specific definition for this concept, or?
No, I would say that what you said as it's quantum interference of heat that we measure. Yeah.
Okay, thank you.
Thank you for the talk. I have a question about strong coupling. And in you mentioned that so far you're considering only weak coupling. And in strong coupling, so what are the formulas we are supposed to use? The only idea that pops into my mind is some kind of mapping.
So your question is what is it good for?
Yeah, what strong coupling?
Okay, so this is another question of definitions, of course. So we would say weak coupling, at least the first experiments that I showed were definitely in the weak coupling, because everything could be described by the lowest order master equation with a transform when the qubit is so this is of the order of 1% or so. The capacity, otherwise you kill the qubit if you increase that further. In the flux qubit, you don't have this limitation, and in our case, by this galvanic connection, we can get now easily to 10% of the energy of the qubit. And I know that in Japan, the Semba et al. Already, like almost 10 years ago, they made couplings which were close to the 100% of the qubit energy. So it's possible to do this. But then, of course, all the game changes in a sense that if you want to make refrigerators in these configurations, you are dealing with a combined system which is subject to your drive. And all what we kind of derived for the weak coupling case is not valid anymore. So on one hand, with a strong coupling, you can transfer, in principle, much more heat in proportion to the coupling, but then the concept is not working necessarily the same way.
Thank you. I have just a small question, which maybe is related to what you just explained. You have a slide on the local versus global approaches.
Yeah.
And I was just wondering, experimentally, how do you switch from a model to another?
Yes. So not in this configuration, not in one sample. But what we can do is this can be controlled by the capacitances here. this can be controlled by the value of the resistance, for instance. Or you can also, if you have here also the extra capacitance, you can vary. So they can be, from sample to sample, you can vary. And these were two different samples, for instance, here. So what matters is the hierarchy between the two. So there's not, both of them are weak couplings in this case.
So in the local case, you need a strong coupling left.
So here the coupling, this one is stronger than this.
I see.
Whereas
okay.
here it's essentially opposite.
Okay, I see. Thank you.
Thanks for the interesting talk. So about also this part, you mentioned that these baths, they have finite heat capacity.
Yes.
So, but you also use master equations to describe them.
Yeah.
So, do you take any precautions so that the state of the bath doesn't change during the experiment?
Sometimes we did something related to the finite non-zero, finite heat capacity, but look, the changes of temperature are very small. So we are kind of, as experimentalists, we think that they are good enough baths. There's a small change in temperature which we can barely see. So we can assume that they are constant temperature. But in principle, it's a very interesting question, how you deal with the master equation with baths which have finite heat capacity. And it is, of course, it is somehow important. Yeah, so it can, especially when we come to this single photon detection capabilities, then it starts to matter. For instance, if you have a single photon detector, calorimeter, it absorbs energy, its temperature changes, it's waiting for the next photon to come, and it is sitting at a different temperature at that time. So this will have even a practical influence.
Thanks.
I would have a question about noise refrigeration. And if I'm not mistaken, you would need to use the noise to perform work in order to cool the system down.
Yeah.
So I would like to know how that exactly would work.
How?
How the noise performs the work for the refrigeration.
How does it do work, you mean?
Yes.
Okay, so it's a good question. So we didn't maybe put it to this context somehow. It's we analyzed it just as a fluctuating bias, so it works as a. Yeah, of course you can find the work if you also evaluate the current that is running through the junction. I think you can do it, but we didn't do it this way.
Is there a finite bias across one of the resistors?
Sorry?
Is there a finite bias across?
Yeah, so of course this is the thing. So for this demonstration, we heat this artificially, of course. So we do work, current times voltage essentially to heat a resistor. But of course the QEI objective would be that you always have some higher temperature parts in your system for free. And can you make use of those to use the waste heat, so to say, to do this? But in here, the work is actually, it's current times voltage on the heating resistor here in this measurement.
Are there more questions? If not, let's thank Jukka again.